All right, welcome. Today, we are diving into an absolutely ingenious engineering trick that, believe it or not, holds up so much of our modern world. We're talking massive bridges, sprawling stadium roofs, all of it. It's a technique that takes one of concrete's biggest weaknesses and, get this, turns it into its greatest strength. So, let's get right into it.
I mean, have you ever really stopped to think about that? How does a material like concrete, which we think of as kind of brittle, stretch for hundreds of feet, supporting all those cars and trucks, not to mention its own incredible weight, without just cracking right in the middle? Well, the secret lies in a powerful and totally invisible squeeze. Okay, so to really get the solution, we first have to understand the problem. And the problem's name is tension. You see, for all of its strengths, regular old concrete has this one critical hidden weakness when you try to pull it apart. And for years, that flaw really limited what we could build. This slide just lays it out perfectly. Squeeze concrete, what we call compression, and it's an absolute rock. It's incredibly strong. But try to stretch it, that's tension, and it fails. Badly. And that stretching is exactly what's happening on the bottom edge of a bridge beam every time a car drives over it, which creates the perfect recipe for disaster. Now, you're probably thinking, wait, what about the steel bars they put inside concrete? The rebar. And that's a great point. But here's the thing. That's a reactive solution. That steel rebar only kicks in and starts doing its job after the concrete around it has already failed and started cracking. Engineers knew there had to be a better, more proactive way to do this. And that better way is what we're calling the pre-squeeze solution. This is really the aha moment of the whole story. Instead of just waiting for tension to show up and cause problems, what if you could just get rid of it from the very beginning? What if you could make it so tension never even has a chance? And here it is, pre-stressed concrete. The name really tells you everything you need to know. We introduce a massive internal squeezing force, that's compression, into the concrete before it ever has to support a single pound. This built-in squeeze is perfectly designed to fight back against any stretching forces that try to pull the concrete apart down the road. So how in the world does this work? Okay, imagine you've got a row of books you want to pick up without a tray. If you just lift them from the ends, they all fall, right? But if you squeeze the ends together really hard, you can lift the whole row as one unit. That's exactly what's happening here. First, super high-strength steel cables, or tendons, are stretched incredibly tight. Think of a guitar string. Then concrete gets poured all around them. After the concrete is rock hard, they release the steel. And that steel desperately wants to shrink back to its original size, and when it does, bam! It transfers all that stored up energy into the concrete as a permanent, powerful squeeze. Now, applying this squeeze isn't a one-size-fits-all kind of deal. Depending on the project, engineers use one of two main methods. And the big difference between them, it just comes down to timing. The difference is all right there in the name. With pre-tensioning, you pull the steel tight before you pour the concrete. Simple enough. With post-tensioning, you actually pour the concrete first, leaving these little hollow tubes running through it. Then you thread the steel cables through and pull them tight after the concrete is already hard. And this is where you can see where each method really shines. Pre-tensioning is perfect for a factory setting, right? You can just churn out identical pieces like railway sleepers or electric poles. Post-tensioning, on the other hand, is the go-to for those massive, one-of-a-kind structures built right there on the construction site. Anytime you see those giant girders being lifted into place for a new bridge, you can bet that's post-tensioning in action. So we've gone through all this effort to pre-squeeze our concrete. What's the payoff? Why is this technique such a game changer? Well, the results are, honestly, they're nothing short of spectacular. 20 to 30 meters, that's up to almost 100 feet. That's the typical span you can get from a single pre-stressed beam. This is what allows architects to create those vast open spaces without a forest of columns getting in the way. It would just be impossible with regular concrete. And the efficiency is just incredible. Because the entire piece of concrete is being held in compression, the whole beam is working for you. There are no lazy parts. This means you can design beams that are 20 to 30% lighter, which saves a ton of material and money. Plus, when it's just doing its normal job, there are basically no cracks and no sagging. The structure stays perfectly stiff. I mean, just look at this comparison. The leap in what you can do is enormous. It's not even a close competition. This is what lets engineers design those beautiful, graceful, sweeping bridges and those roofs that look impossibly thin. It's all thanks to that invisible squeeze. But, like with anything in the real world, it's not quite perfect. That incredibly powerful squeeze that we put into the concrete at the very beginning, well, it doesn't stay at 100% strength forever. And engineers have to be incredibly smart and account for something they call losses. Now, here's the really clever part. Engineers plan for all of this right from the start. They actually over-tension the steel on purpose. It's like tuning a guitar string just a little bit sharp because you know it's going to settle. They know that over time, things like the natural shrinking of the concrete and tiny amounts of friction are going to cause that squeeze to fade just a little bit. By planning for it, they make sure the structure stays perfectly safe for its entire life.
So the next time you're driving over a really long bridge or sitting under a massive stadium roof, just take a second, remember that what's really holding it all up is this powerful, invisible squeeze that was put there on purpose. It kind of makes you wonder, doesn't it? What other invisible forces are out there, shaping the world all around us?